Okay. Hello, everyone. Today is our presentations of Group 3 about projects, about forecasting of time series using ARIMA and Holt-Winter. Our Group 3 uh, is Nguyen Anh and Pham Hùng. Our table of contents have four parts. About first one is introductions about the electricity demands and a literature review. The next one is the data visualizations. Next one is the results about the forecasting using the ARIMA and Holt-Winter and regressions. And finally is the conclusions. First one, we come to the about the electricity demand forecastings. We all know that the global power demand is growing strongly in 2024, uh, and driven by electrifications, marking the beginning of a new age of electricity. So, energy demand forecasting will estimate the future electricity consumptions using available data. It is include not only the amount but also the location and timing of demand. And forecasts are so essential for financials and operational to planning in the distribution system. And forecasting is divided like by time horizon into three parts: the short term, medium term, and long term. But about ARIMA, ARIMA is stands for Autoregressive Integrated Moving Average and is a technique for time series analysis and for forecasting possible future values of a time series. The ARIMA models will combine three components: the AR autoregression to depend on previous value of the series, the I integrated use different things to make the series become stationary. The MA, the moving average, depends on the past forecast errors. These ARIMA models would typically denoted as PDQ, which in which P is the number of black observation in the AR part. The D number of time series different things is applied to make the series stationary. And finally, the Q, the number of black forecast error in the moving average part. The Holt-Winter is a model of time series behavior to forecasting. Uh, when we forecast something, we always require a model, and this Holt-Winter is the very interesting way to forecasting using three aspects of the time series: a typical values, a slope over time, and a cyclical repeating patterns, the seasonality. The Holt-Winter method uses exponential smoothing to encode lots of values from the past and use them to predict typical values for the present and future. Holt-Winter models have two types, the additive seasonality models and the multiplicative seasonality model. In the regression part, we have four regression things to do. To using here, first one to the linear regressions is used to predict the values of a variable based on the values of another variable. The variable you want to predict is called the dependent variable. The variable you're using to predict the other variable's value is called the independent variable. This form of analysis estimated the coefficients of the linear equations involving one or more independent variable that best predict the values of the dependent variable. Linear regression models are relatively simple and provide an easy-to-interpret mathematical formula that can generate predictions. Linear regressions can be applied to various areas in business and academic study. The next one, the light GBM, it stands for Light Gradient Boosting Machine, is the high-performance boosting framework optimized for speed, efficiency, and scalability. It handles large data sets pretty good and support parallel computing and use histogram-based and leap-wise tree growth techniques. It also uses exclusive feature bundling to reduce dimensionalities and improve performance, especially on sparse data. about the random forest regressions, it builds multiple decision trees using random subset of data and random subset of feature sampling to ensure model diversity. Each tree makes the predictions, and the final output is the average of all tree predictions, a process called aggregation. The XGBoost is a powerful supervised regression method that uses an objective function to combining a loss function and regularizations to measure prediction error. It is an example learning method that builds multiple weak-based learner. These learners, when combined, cancel out errors and improve overall predictions accuracy. We're moving on to the block diagram. In our slides, we have two block diagrams of when we're using ARIMA and Holt-Winter. The first one, as you can see here, is the block diagram of ARIMA and Holt-Winter models, and the next one is the block diagram of regressions. As you can see here, we will be as you can see here, we will start the provide block diagram will illustrate a systematic methodology for time series forecasting by comparing an ARIMA model against a Holt-Winter model. The process will commence by ingesting the electrical demands input data, which is then subjected to the comprehensive data pre-processing phase that include handling any missing values, converting the date column into a proper date time index, performing feature energy engineering, and setting a consistent hourly frequency for a time series. The following in the pre-processing stage, the data is split into training, testing, and validation set. At this stage, the methodology was split into two parallel paths. The first path for the ARIMA models involves checking for stationary with ADF test, aka the Ali-Fuller test, to testing it, applying different things if necessary, using an auto-ARIMA function to find optimal model order, and then training and evaluating the ARIMA max models before performing residual diagnostic. The second part configured the Holt-Winter model with an additive trend and seasonality, set it to handle dual daily, 20 and weekly seasonal periods, and then proceed with training and evaluations. These two processes will converge at a model comparison step, where metrics like MAE, RMSE, and MAPE are used to select the best performing models. In the final phase, this model is retrained on a combined dataset of training and testing data before it generates a final forecast on the unseen validation data. The entire process will conclude by evaluating this final forecast and outputting the result and visualizations. The next one about the regressions. This block diagram will details a machine learning workflow for forecasting electricity demand using regression models. The process will start by loading the input data, electric demand, followed by a comprehensive feature engineering phase where time-based feature, lag feature for demand at 3 plus 24 and 3 plus 168, and rolling window feature like rolling mean and standard deviations are created, and any missing values are handled. Subsequently, the data set is defined by separating it into a feature set and the target variable, which is demand. This data is also split into training and testing set, ensuring software equal to false to maintain the order. The feature then will scaling using a standard scaler, which is fed on the training data and then used to transform both the training and testing sets. The scale training data is then used to train 4 distinct regression models in parallel, using linear regression, random forest, XGBoost, and like GVM regressions. Each of these trained models will generate predictions on the scale test, and these predictions are evaluated against the actual test values using a suite of metrics include MAE, RMSE, and MAPE. Based on these evaluations, the matrix are compared to citing the best performing model. Finally, for this best model, visualizations such as actual versus predicts plot and a scatter plot are generated, and a summary of the result is written into output before the process concludes. Moving on to the next about the data visualizations, we will take a look at the overview of electric data domain. Here is the in this figure, 2.1 is the overview of the data set. As you can see, it's because it's a really a big data. So for convenience to analysis and visualizations, we will make some small we will make some adjustments by changing the sample time into 1 hour per data instead of 30 minutes per data. The demand in 1 hour is total time and temperature is average between two sample times every 30 minutes. The data has been collected from the 31st December 2011 to 31st December 2014, about totally 26,300 for observations. In the figure 2.2 is the overall of our data about electric demand over time. This time series provide a visualization of electricity demand over 3 years from January 2012 through December 2014. This data will reveal powerful overlapping patterns that are fundamental to understanding energy consumption. Seasonality is evident. Around mid-years, electricity demand will spike and create a very high peak. Springs and falls valleys. There is a slight increase in demand during the winter months, mid around January and February, but this peak is significantly lower than the summer peak. This suggests that heating demand also increased electricity use, but not as much as cooling demand. About figure 2.3 is the average demand in Delhi. For the relationship between the hour and day, we can see two peaks from about 11 p.m. the previous day to 5 a.m. the following day. Electricity demand is quite high and stable. In the morning, starting at 6 a.m., the demand spike and reach its highest peak of the day at about 8 a.m. After the morning peak, demand begin to decline, slow down, especially after 12 noon, and it reached its lowest point of the day around 4 to 5 a.m. 4 to 5 p.m. After 5 p.m., the demand will increase sharply again because this peak reached its highest point around 9 p.m. to 11 p.m. This is the peak of the residential load. In this figure, 2.4 is the electric demand by hour of day and day of week. For the hour of day, in the morning peak around 7 to 9 a.m., the box are very high, indicating a sharp increase in electricity supply. In particular, the box at hour 8 and 9 are very high, confirming that this is an industrial peak. But in the midday, from 10 a.m., the demand starts to decrease and the box at 3 to 5 p.m. are the lowest, indicating that this is the time of day when electricity will consumption is at its lowest. Of the evening peak around 8 to 9 p.m., the demand will rebound sharply, creating a second peak due to the household load. High demand hours, the box are relatively short. It means that the demand at this time is quite stable and predictable. For the day of week, from Tuesday to Fridays, the demand is high and relatively similar. The box are located high, indicating stable electricity consumption for productions and business. And in Monday, the demand is slightly lower than other day of the week. This may be because of some production activity needing time to restart at the beginning of the week. And at the weekend, about Saturday and Sunday, the demand is significantly reduced. The Saturday has lower demand than other day of the week, and the Sunday has the lowest demand. In this figure 2.5, the distribution of electricity demand by month of the year. This is a box plot that illustrates the distribution of electricity demand for each month of the year from January to December. In summer, summer peak, the box for June and July and August are the highest on the chart. July has the highest median demand. In winter, January, February, and December show a secondary lower level in demand. This corresponds to the winter season. Winter season. The increased demand is due to electric heating, while significantly the heating load is clearly less impactful than the cooling load during the summer. In spring and autumn, the box like April, October, November are the lowest on the chart. This month will represent the mild season of spring and autumn. The weather is comfortable, it will minimizing the need for both heating and cooling. In this figure 2.5, the demand with comparison between I will comparison the demand in weekday and weekends, and we can see the lower demand is on the weekends. The most apparent takeaway is that the entire box for weekends is positioned lower than the box for weekday. This clearly shows that on average, electric demand is significantly lower during the weekends. In the figure 2.7, the plot will illustrate the relationship between the temperature and the electric demand. Each dot on the plot will represent a single point in time where a specific temperature will record along with the corresponding electricity demand. The plot reveals a distant, non-linear relationship between these two variables, often described as a U-shape or a smile shape. In low temperature zone, on the left side of the graph, as the temperature increases, the electric demand will tend to decrease. This represents the heating demand. When it's cold, people will use heater, heat pump, and other heating applications which consume a significant amount of electricity. The colder it gets, the more heating is required, thus increasing the demand. In comfort zone, the electric demand is at its lowest level because people feel comfortable without relying on energy. So it will be the lowest. On the right, in the high temperature zone, as temperature rise, the demand will increase sharply. This relationship is very strong. The higher the temperature, the higher the demand. Moving up to the stationary test. As you know that a time series is stationary if its statistical properties like mean, variable, variance, and autocorrelation are all constant over time. It doesn't have a trend and its cyclical patterns are stable. Most especially ARIMA will need the time series to become stationary to forecasting. So how do we know if a time series is stationary or not? We will use the ADF test, aka the AD Fuller test, to testing it. The Augment-Dickey Fuller is designed to test um, in the to test the ADF will um test as a skeptical prosecutor. Its starting assumptions is that the data is guilty or being non-stationary. It looks for strong evidence to prove otherwise. If the p-value is less than 0.05, I can say that the data is stationary. As you can see in the picture here, um, we have the result of the open Dickey-Fuller test. The p-values is equal to 0 since this is less than 0.05. The ADF test can say that the data is stationary. So we no need to differencing. In As you can see here, I using the decompositions to split the uh, time series into three parts. The chain into three to change the chain seasonals and remainder. Uh, Moving on to the next one is the result. In this result, I will using to create the models for making ARIMA and Holt-Winter forecasting. I will using the AI Studio software, and I will create simple models. We have the input is 1 hour electric demand data, and using the operator is forecast validations. Inside the training part, we'll use the ARIMA or Holt-Winter, and the testing part will use the performance regression operator. First one in using the ARIMA to forecasting, because to make sure how to using the ARIMA, we need to make sure that the data is stationarity. And as you know that we have the ADF Fuller test, and we have the result here. That means this data is already stationarity, so we no need to do the differencings. So I will assume that the D will equal to 0. And to choose the values of the P and Q, I will use the ACF and PACF chart to find its values. As you can see in the first one, this the PACF values. The first few lags will show that strong values, indicating a clear relationship with recent data. So I choose the P equal to 2. And the next one is the ACF. And as you can see here, the bar decreased gradually without sharp drop. And since there's no strong spike, I think a small value of 3 equal to 0 equal to 1 is makes sense. After that, we will choose the value of the forecast validations. Uh, I want the I choose the window size equal to 168 equal to 7 days, and step size equal to 1, and horizon size equal to 24. Uh, it means that I will forecasting for 1 day, like 24 hours. And after choosing PDQ, I have come to conclusion that ARIMA I will using in here is the 201. And you can see here, this is our result here with absolute error and relative error. The relative error is pretty low, lower than 20%, and I think that my result is pretty correct, pretty good. Moving up next to I will come closer to the data here. I will choose the positions 1 and 24. As you can see here in the plot here, the green line is the actual demand. The blue line is the forecast, and the position 1, and the flat line blue line in the middle of the figure 7 is the forecast of position 24. As you can see here in position 1, the blue one and the actual demand and forecast demand are mostly follow each other closely to show that our forecast of position 1 is pretty close to the actual demand. But in position 24, the forecasting model show a significant drop in accuracy. It struggled to stay accurate over a longer period, especially with long time series that contain strong seasonality and trend. And Oh, moving up here. And here I calculate the MAE and RMAE and MAP of the 24 positions I have of my result. As you can see here, the model performed pretty good from positions 10 onward, especially in position 20 to 24, where MAP is very low. Higher errors in early position. And overall, the model show reasonable accuracy, especially for short-range hourly forecast. After a forecast of 1 day using ARIMA, I will forecast 7 days. And I choose the horizon size equal to 168 because it equals to 168 hours equal to 7 days. And I have the result here is the relative errors is the 15.20%. It's also really low to show that our model is working pretty good. In the plot here, the green line is actual domain. The black line is the forecast of position 6. The flat yellow line is the position 72, and the blue line is the forecast of the positions 168. As you can see here, the position 6 is like the early stage is pretty good and capturing the demand cycle and short-term fluctuation effectively. However, we can see the problem as long the more it go further, the more it struggle to capture the cycle. It rapidly degrade from medium and long horizon of positions 72 and 168, producing flat and non-reactive forecast. And in the MAE, RMAE, and MAP calculate, the model performed poorly in the early to mid, and the forecast accuracy. This suggests that the model may be biased toward long-term average change or better suited to flatter demand curve at higher forecast positions. Moving up to the Holt-Winter, and to choosing the Holt-Winter is choosing the parameter for the Holt-Winter is pretty easier than the ARIMA, and the parameter of forecast variations will still the same for 1 hour with horizons equal to 24. And I choose the alpha equal to 0.5, the beta 0.1, the gamma 0.5, and I choose the C analysis using additive. And the lag of period with 24. After that, I have the result here with relative error is 50.43%. It's also really low, and it shows that our model is work pretty good. And as you can see here, the in position one is the blue line, and the position 4 is the yellow line. As you can see here, the position one will follow the closely to actual demand. It show that it works pretty good. But in position 24, the forecast is become bigger and become instability and overreactions, indicating that the model are struggle with longer term forecasting. And the model in here is the calculate of MAE, RMAE, and MAP. And the model would deliver very accurate short-term forecast. And from position 9 onward, the forecast accuracy started to decline, reaching peak error at position 16 to 18, and position 21 to 23 show improved performance again, suggesting the models handle certain stable periods better. Moving up to the using the Holt-Winter forecast for 7 days, And I changed the horizon size to 168, and seasonality is multiplicative to make sure the data the result is become the relative error is become smaller to make the data work pretty good, better. But in here we have a pretty big relative errors equal to 48.52%. It's pretty big, and it showed that our models are working not pretty good, and makes so many unstable stability. And as you can see here, the models work very well at short horizon, the position one, as you the red one, the blue one. But from the position as 84, the red one, the quality will start to degrade with increasing noise and phase shift. And finally, the position 168, the yellow one, the model become unstable and inaccurate, reflecting the limitation of the current forecasting setup for long-term predictions. Uh, The models forecast well for short-term horizons, with low MAP. However, the error rise sharply at 30 and uh, peaking between position 66. And finally, we're moving on after forecasting with ARIMA and Holt-Winter review comes the regression part. After cross validations, we have the table in here. As you can see here, we regression use regressions with time with position 1, position 24, and position 168 using the four models regressions: linear, random forest, line GBM, and XGBoost. And as you can see here, the best model is line GBM because it had small MAE, small MAE RMSE, we had a better MAE, RMSE, and MAPE more than others models. The next step is using the hyperparametric tunings, because the next step involves optimizing the line GBM models through the hyperparameter tuning using grid search CV. For each forecast horizons, the model tests various parameter combinations to find the best setting. Time series split is used for cross-validation to avoid data leak by training on past data and validating on future data. The process selects the configurations with the lowest mean absolute error, resulting in a well-tuned model tailored for each specific forecasting task. And as you can see here, after parameter tuning, we have the result in the figure 3.19. Um, and finally, here is the result of forecasting after parametric tuning in 24 hours and in 168 hours. And as you can see here, it gets better and better using the line GBM regressions. And finally, come the conclusions. As you can see here, the ARIMA is performed the worst, especially for long-term forecasts, producing flat lines due to lack of differencings or non-stationary data. Its failure stem from an inability to model trend and exclude external variable. Switching to Sarimax and including variables like temperature and holiday could significantly improve the performance. The Holt-Winter is the best one. We capture short-term seasonality, but quickly became unstable for longer horizons. So its main limitations in ability to cooperate external variables, which are crucial for electricity demand influenced by temperature and calendar effects. About the best regressions, the large GBM is delivered the best results thanks to effective feature engineering. It's achieved much lower MAE compared to ARIMA and Holt-Winter. Its strength lies in using external factors and learning complex patterns. Finally, the machine learning regression model, especially like GBM, will outperform classical time series model by integrating external variables and engineered features. They offer more accurate, stable, and practical forecasts for short and medium terms operational planning. Thank you for listening to our presentations. Is anyone have any questions?
I have a question.
Yes.
In your part 2, you have um can you back to part 2? Where you identifying ADF and KPSS?
Could you repeat the questions?
Cái phần kiểm định ADF với cả KPSS ấy.
Yes.
I'm seeing you using D equals
ADF.
0. Yeah.
Yes.
Like, can you explaining how you use like the differencing, not using differencing here?
It seems like um, I using the Dickey Fuller test to testing it whether it's stationary or not, and it seems like the result is showing that the results this time series is stationary. So because it is already stationary, I think we don't need different things. So I choose the D equal to 0.
So it's only depends on your simulation, right?
Yes, I run this. We run this Dickey Fuller test using Python code.
Okay. Then about the Holt-Winters, can you identify why the alpha, beta, and gamma? How do you identify those? To identify the alpha, beta, and gamma.
Uh, to choosing the parameter of alpha, beta, and gamma, I using the default. Uh, I choosing the default parameter of AI Studio because it's work pretty good. Uh,
Maybe for my sense, not for any one parameter.
I think it worked perfectly. It have a result. We work perfectly with forecasting.
So simulation too. Okay. Do you use hypertuning for regression?
Yes, I have a hyperparameter past
Yeah.
before find the best model.
Only for
Yeah,
the best model, right? Yeah.
yeah. I just hyperparameter past for the best model. In this my result is like ZBR.
Yeah. Okay, that's all my question. Thank you.
Okay.